Welcome to Copernicus AI, Frontiers of Science. I'm Matilda, and today we're exploring new perspectives on the Lac Operon. Adam, what makes the recent research in this area so revolutionary?
Thanks, Matilda. The real paradigm shift comes from applying Boolean network models to understand the Lac Operon's behavior. Traditionally, differential equations were the go-to method. But papers like the one by Andy Jenkins and Matthew Macaulay, Bistability and Asynchrony, in a Boolean model of the L-Arabino's operon in Escherichia coli, show how Boolean models can capture the essential dynamics with simpler, more intuitive frameworks. Available at https://pubmed.ncbi.nlm.nih.gov 286399170.
So, instead of complex equations, we're using a simpler on-off switch approach? What are the advantages of that?
Exactly. Boolean models represent gene states as either active or inactive, making it easier to analyze network behavior under different conditions. Jenkins and Macaulay also have another paper, Synchrony, in a Boolean network model of the L-Arabino's operon in Escherichia coli, available on AAR-Archive, which further explores the dynamics using this method. You can find it at http://rexev.org, ABS 1611-2656V1. This approach allows researchers to explore the system's attractors or stable states, which represent the long-term behavior of the gene regulatory network.
Attractors, like what the system settles into? So, how does this new perspective change our understanding of the Lac Operon?
It provides a different lens for examining phenomena like bistability, where the system can exist in two distinct stable states. Traditionally, bistability in the Lac Operon was understood through the lens of differential equations. However, Stigler and Velas-Cuba show in their paper Network Topology as a driver of bistability in the Lac Operon, available on ARKIF, that network topology plays a crucial role. This Boolean approach helps identify key components that drive these different states. The URL is http://rxiv.org, ABS 0807-299995V1.
Is there a connection between these models and controlling these gene networks?
Absolutely. There's research exploring control strategies within these Boolean networks. For instance, Lin Lin, Jinde Cao, and Jie Zhong et al. Explore necessary and sufficient conditions for event-triggered set stabilizability of Markovian jump logical networks. https://pubmed.ncbi.nlmm.nih.gov 370748992E. They're looking at how to use minimal interventions to steer the network towards desired states, which has huge implications for synthetic biology and potentially even disease treatment.
That's quite a leap. What other applications might this kind of modeling have?
The principles extend beyond the Lac Operon. Researchers are using similar Boolean network approaches to understand other complex biological systems. Mortveit and Peterson, for instance, explore attractor stability in finite asynchronous biological system models, https://pubmed.ncbi.nlm.nih.gov 326565004, and also in another paper available on ARXIV, http://arXiv.org, ABS 2208-11732V1. While not directly about the Lac Operon, their work provides mathematical tools for analyzing long-term dynamics in other biological models. These tools enable analysis of the effect of perturbations or interventions on biological system behavior.
Are there any limitations to these models? What don't they capture?
Boolean models are, by design, simplifications. They don't account for continuous variations in gene expression levels or the complexities of protein interactions. However, they offer a valuable abstraction for understanding the core regulatory logic.
What's the next big question in this field?
A key area is integrating these Boolean models with other types of data, like time series gene expression data. This would help refine the models and make them more predictive. Another avenue is exploring the stochastic nature of gene regulation. Toyota and Wu's paper on maximum likelihood state estimators in probabilistic Boolean control networks, https pubmed.ncbi.nlm.nih.gov 348606570, addresses this by considering the stochastic switching of logical update functions. Understanding these stochastic elements will be critical for designing robust and reliable control strategies.
Adam, this has been incredibly insightful. Thank you for breaking down this groundbreaking research. It sounds like these Boolean networks are revolutionizing how we understand and potentially control genetic systems, moving us closer to designing biological systems with predictable outcomes.
My pleasure, Matilda. It's a really exciting field with enormous potential.